Hey guys, so today we're going to be looking at alloys. Alloys are simply solid solutions, so they connect very directly to the unit we're currently in. And so we're going to talk today about the different types of alloys, and we're going to be talking about their different types of properties. So first of all, a quick definition. Alloys are going to be mixtures of metals that are essentially solid solutions. Now the way we can think about this is if a solution is a homogeneous mixture of multiple components, an alloy is the same. Biggest thing about alloys is the bonding involved in an alloy is going to be metallic bonding, and they are solid alloys. So the key here in terms of alloys is understanding that they're simply homogeneous solutions. And as with any homogeneous solution, the properties involved are going to be somewhat in between the two component parts of the solution. One example of an alloy that we're actually going to utilize in a laboratory here in class is going to be brass. Brass is a mixture of copper and zinc. And so what it's going to be able to do by creating an alloy is actually combine the properties of both atoms involved or both elements involved in making that compound. Brass is a little bit less malleable than copper, but retains many of the properties of copper, including color, conductive character, and many of the malleability properties that zinc does not have. So by adding zinc to the copper, we create brass, which combines the two properties to some extent, allowing us to exploit different factors of each metal. Another important thing about alloys is understanding that although almost all alloys that we discuss in class are made of metals only, some alloys actually are made of non-metal. For instance, steel is a combination of iron with carbon, and in many other cases, other metals as well. But the key here is that by adding carbon and non-metal, we actually are going to take the iron and make it much, much stronger. So not all alloys that we're going to discuss are going to be purely metal. Some are going to be combinations of metals with some non-metal atoms in there. Now, one important part of understanding alloys is recognizing that there are two different types of alloys. Alloys can come in either substitutional form or interstitial form. Now, substitutional, as the name suggests, means that the atom of one metal essentially is simply replacing an atom of the other metal. Interstitial suggests that the metal is being added in between the atoms of the other metal. Now, it's hard to do this without visualizing, so let's take a look at these two particle diagrams. On the left, you see a substitutional alloy, and you can see the two different colors that represent two different elements. They're effectively the same size. It doesn't have to be exactly the same size, just fairly close. However, on the right, it's an interstitial alloy. An interstitial alloy, you can see that the color of the small dots is different than the big dots. This suggests that the little ones are a totally different metal element than the big ones. That suggests interstitial. Notice how the small atoms are found actually in between the gaps between the large atoms. In terms of alloys, there are a number of different ways we can really be presented with an alloy problem in chemistry this year. The first one is going to be simply determining whether an alloy is going to be an interstitial or substitutional alloy. Now, connected to that is a really common type of problem that's going to ask you to actually draw a particle diagram of an alloy. They're going to give you the relative size of two atoms involved, and it's going to be your job to make the decision whether to draw it as substitutional or interstitial and how to diagram it out such that remember, in a homogeneous solution, the atoms are going to be evenly and somewhat randomly distributed throughout the entirety of the compound. So with alloys, drawing particle diagrams is definitely a problem that you're going to see this year. The next common type of problem is going to be asking you to predict the properties of an alloy given the properties of the component parts. So let's say we're asked to predict the properties of brass given certain properties of copper and zinc, and knowing that we are going to have a certain ratio of copper and a certain ratio of zinc in the brass, you're going to be asked to predict what's the most likely property for that brass alloy. The next kind of question that you're often going to see in terms of alloys is going to be a question about how an alloy will react either similarly or differently, and many times this is going to be based on a particle diagram. Now remember, any metal will only react on the surface. Alloys are no different. So only the surface area that's exposed is going to be reactive, and so the question's often going to come down to how will it react based on the elements that are exposed at the surface. So let's take a look at our first type of practice problem. Now in this problem, we're going to be looking at whether an alloy would be predicted to be substitutional or interstitial. Now, sterling silver is not pure silver. Sterling silver is an alloy of both silver and copper atoms. Now, the copper is actually added to silver, pure silver, because pure silver is too soft to actually be functional in terms of silverware or plates, or even for that matter, rings or jewelry. So we use sterling silver oftentimes because the copper provides an extra hardness factor that the silver by itself would not have. In addition, the copper allows the silver to retain its luster and ductility, so it can be molded and modified into plates and silverware and jewelry and the sort. Now, if we're looking at the values given for the radii, the radius of a silver atom is 172 picometers, whereas of copper it's 128 picometers. Now, if you want to think about this in terms of relative sizes, these are off by a little bit, but certainly not by a lot. Because the sizes of these radii are close enough, we actually would consider this to be more likely to be a substitutional alloy, and in fact it is. It is in fact a substitutional alloy. When the radii are similar enough, we would consider it to be substitutional. If the radii are dramatically different, it's more likely to be interstitial. Now in our second problem here, we're going to be looking at steel. Now, steel is kind of a generic term. There are many types of steel. In some steels you have added carbon, in some steels you have added manganese or vanadium. You can add essentially anything to iron in order to create steel, but the major component of steel is always going to be iron, and a minor component will be non-metals in many cases, such as carbon. Now, one of the most important things to creating steel is the understanding that steel is used in construction. It has to be very hard, but still needs to retain some ductility and still needs to be able to retain some malleability while at the same time retaining that strength. So you create steel using a very impressive and very, very complex process of combining in non-metals with your iron. Now, non-metals, if you remember on the periodic table and we look at atomic size, non-metals such as carbon are extremely small, very small, relatively speaking, especially compared to our metals such as iron. Therefore, because of the fact that we know, based off of what we know about periodic table trends and atomic radii, that carbon is going to be much smaller than iron. And even though we're not directly given the size, the radii, we can come to the determination that this will in fact be an interstitial alloy because of what we know about atomic radii, given the number of energy levels and the effective nuclear charge of each of them. All right, so let's take a look at this practice problem. In this one, I'm asked to rank the relative densities of my two substances. Now, in this case, I have pure iron or steel. In this case, it's a combination of iron and carbon. And you can see the carbons, the little black dots that are found in between the atoms of iron. That means it's an interstitial alloy. Now, in the case of this alloy, if I were to try to rank the densities, remember, it's based off of mass per unit volume. Interstitial alloys, the volume's not changing dramatically, but the mass is. Because I'm using those little gaps in between the iron atoms to fit those carbon atoms, I have more mass per unit volume, and as such, the alloy, in this case, the steel, would be more dense than the pure iron itself. All right, let's take a look at this problem. This is a problem where we're going to take an alloy of copper and iron, and we're going to look and see how it would react in this situation with air. This is a common type of problem that you're going to see, but you're not oftentimes going to be asked to draw the particle diagram by yourself. Often it's going to be pick the particle diagram that most likely represents what's actually going on. So in this situation, we have this iron-copper alloy, and it's going to be reacting with the oxygen in the air. Specifically, the iron atoms are going to react with the oxygen in the air to produce iron oxide, better known as rust. Now, iron oxide is FeO2. This is iron 4 oxide, which is the most common form. Now, iron oxide is going to create a situation where we have an iron atom bound to 2 oxygen atoms, which means that if we're going to draw a particle diagram, we need to make sure that FeO2 has 1 iron atom and 2 oxygen atoms associated with it. Also, you'll notice that iron atoms that are internal generally aren't reacting. Very, 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 very rarely will you have an oxygen atom capable of penetrating internally. But though some instances where it could happen is when a reaction at the surface has already happened. Iron oxide creates a more permeable surface. It also has different solubility. And as a result, you might get an internal reaction here or there. So it's not impossible to get internal reactions in the case of iron oxide. It's just rare. If you see oxygen strewn throughout the internal, we know it's wrong. It's got to be on the outside, and it's got to be in the right relationship in terms of the molar ratio. So when you're looking at these particle diagrams to make a determination of what's the most likely one to choose, you have to identify size of atoms, you have to decide mole ratio, you have to determine whether it's on the surface or internal, and you also have to determine which element are you actually going to be reacting with. So all of these things are going to play into a question like this. So they're not exceptionally easy, but like I said, rarely will you have to come up with a particle diagram by yourself. All right, so that wraps up today's video. In today's video, remember, we learned about alloys, specifically talking about the differences between substitutional and interstitial alloys, and talking about how we can solve the various types of problems associated with alloys, including drawing them as particle diagrams or looking at particle diagrams to make a determination of how they're going to react, or being able to actually predict the properties of alloys given what we know about their component parts. I'd like to thank you guys so much for watching this video, and I'd like to thank Elizabeth Bunker, who wrote, filmed, and edited it. I'll see you guys in the next one.